Have you ever built a Bayesian model, you hit run, and then you just stare at your screen wondering what went wrong? Sometimes you get nothing, sometimes you get total nonsense. Well, if that sounds familiar, this one's for you. Today, we're going to dig into why your MCMC model might be failing, and more importantly, what you can actually do about it. Yeah, this screen. We've all been there, right? You're staring at it, you're waiting for your sampler to do its thing, but the chains just won't converge. It is one of the most frustrating things in statistical modeling. But here's the thing, it's probably not your fault. You've actually just run into a fundamental problem with math itself. And that brings us to our first big idea, what I like to call the wall of complexity. This is that point where all the beautiful, elegant math we learn in textbooks just completely shatters when it meets a messy, real-world problem. So what is this wall? Well, it's the point where the math just becomes physically impossible to solve. Seriously. See, as you add more and more variables to your model, to make it more realistic, the search space of possible answers just explodes. It turns into this crazy high-dimensional landscape. Trying to find the right answer with pure calculus is like trying to find one specific grain of sand on a beach the size of a planet. It's just not going to happen. This complexity trap really has two parts. First, there's the denominator problem. In Bayesian stats, there's this one calculation, an integral, that basically needs to find the total area under a curve, and with every single variable you add, that calculation gets exponentially harder. Then you've got the curse of dimensionality. Get this, with 50 or more parameters in your model, there are literally more possible solutions to check than there are atoms in the entire known universe. So the math isn't just hard, it is physically impossible. So if perfect math is off the table, what do? We have to change our strategy completely. Think of it like this. On the left, you have exact inference. That's like using perfect geometry to find the volume of a simple swimming pool. It's 100% accurate, but it only works for really simple shapes. On the right, you've got MCMC simulation. Here, we totally give up on perfect math. Instead, we just throw, say, 10,000 pebbles into the pool and see where they land. By checking the pattern of those pebbles, we can get an incredibly good approximation of the pool shape, no matter how weird and complex it is. Now, this is super important because people get this mixed up all the time. You have to understand the difference between the problem itself and the tool you're using to solve it. So let's talk about the blueprint versus the engine. Okay, first stop you have the Bayesian network. This is the blueprint for your model, or you can think of it as the map of your problem. It's just a diagram showing how all the different variables are connected to each other. You know, how diet and exercise might influence blood pressure. This blueprint is the what your model actually is. Then you have MCMC. This is the engine. It's the vehicle you use to actually explore that map you just drew. So when the map gets way too complicated to understand all at once, you fire up the MCMC engine to drive around and figure out what the terrain looks like. MCMC is the how you're going to get your answers. So to put it simply, a Bayesian network is your model structure. Its goal is to define relationships. MCMC is a computational method. Its goal is to estimate probabilities based on that structure. The key is you don't choose one or the other. You use the MCMC engine on your Bayesian network blueprint. They work together. All right, so we've decided we need an MCMC engine. But not all engines are created equal, not by a long shot. Let's take a look at the physics of sampling to see how these things have evolved from kind of clumsy random walks to these incredibly powerful physics-based explorers we have today. The very first MCMC algorithms are often called a drunkard's walk, and it's a perfect name. Imagine a hiker, blindfolded, trying to find the highest peak in a huge mountain range. They just take one tiny, random step and then check if they went uphill. It sort of works, but it is painfully inefficient. In a really complex space, our poor hiker is just going to get lost. Now, what if instead of a blindfolded hiker, we had a frictionless hockey puck sliding around on that same landscape? That's the big idea behind Hamiltonian Monte Carlo, or HMC. We basically give our sampler momentum. We give it kinetic energy. And it uses the physics of the landscape, the slopes and valleys, to just glide across huge distances in one single efficient move. It's not just wandering around anymore. It's exploring with purpose. But wait, it gets even smarter. The gold standard today is called NUTS, the No U-Turn Sampler. And you can think of it as an autopilot for that hockey puck. It intelligently figures out exactly how far the puck should travel before it stops, which keeps it from wasting a ton of energy by accidentally making a U-turn and going back where it came from. This little detail is the secret weapon under the hood of almost all modern Bayesian software. It's what makes this stuff actually practical to use. So you've run your fancy nut sampler. The computer's done its thing. How in the world do you know if it actually worked? Well, welcome to the diagnostic lab. This is where we learn to read the results and figure out if we can trust our model. And the single most important tool you've got for this is called the trace plot. You can think of it like an EKG for your model's health. It shows you the value of a parameter at every single step of the simulation. It's literally a window into the sampler's journey through your model's landscape.
And this is what you want to see. This is the goal. A healthy trace plot looks like a fat, fuzzy caterpillar. It's just a dense, horizontal band of what looks like noise with no real pattern to it. This tells you the sampler is moving around and exploring all the important parts of the map really well. We call this good mixing. And when you see this, it means your sampler is healthy and your results are reliable.
Now, you also have to know the red flags. If your trace plot looks like a jagged staircase, that means your sampler is getting stuck in certain spots and isn't exploring very well. And if you see a drifting trend where it's just going up or down, that's even worse. That means it hasn't even found the right area to explore yet. If you see either of these, your model is not done cooking. You absolutely cannot trust the results. Okay. This brings us to one final, really high-level decision that everyone doing this work has to make. It's the ultimate trade-off between getting the perfect answer and getting a good enough answer right now. So here we're comparing MCMC, which we've been talking all about, to its main alternative, variational inference, or VI. Think of MCMC as the master crafter. It's totally unbiased, and if you give it enough time, it will give you the 100% correct answer. But it can be really slow. VI, on the other hand, is the speed demon. It's an approximation, so it's technically biased, but it is blazing fast. The choice is simple. If you're launching a rocket to Mars, you use MCMC. If you're building a recommendation engine for 1 million users, you're probably going to use VI.
So if you remember just one thing from all this, let it be this simple idea. Use math to draw the map of your problem. But when that map gets too complicated, you need to use MCMC for the journey.
And that really just leaves us with one final question for you to think about in your own work. What's actually more valuable for your project? A 95% accurate answer that you can get right now, or a 100% accurate answer that you'll have to wait until tomorrow for? The answer to that question will tell you exactly which of these amazing tools is the right one for the job. Thanks for digging into this with me.